All right, folks, in this video, we'll be looking at the start of calculus in complex variables. And that starts off with limits and continuity of functions. Okay, so we need to recall what limits of a function is in Calc 1, right? So really, this is the mathematical notation of what a limit is in calculus, right? So we say that so we say so the limit as x gets close to a equals to L. So we're looking at the behavior of a function, right? So this will look at two different paths, right? In single variable calculus, right? So so this is for number one, this means the limit as x gets close to a on the left equals to L. And this means the limit as x approaches a from the right of f of x equals to L. Then your limit does equal to L, right? So that's one way to show your limit exists. So graphically, if I have this function, let's say, right? And if I approach A, let me label out these parts here. So if I approach A in this direction, right, this will correspond to points that are on this portion of the function, right? And if I approach A this way from the right, this will correspond to points on the curve, on that portion of the curve, right? And this will be L, right? So it's sort of what's called a call and response action, right? So if I approach A from values that are less than A and it equals to L, and if I approach A where values are bigger than A, and if it equals to the same number, then we can definitely say that the limit equals to L. So therefore, your limit exists, right? Otherwise, if they don't equal, the limit does not exist. Okay. There's also what is called the epsilon delta definition of a limit. You don't have to write this down, but and it goes like this. So for all epsilon greater than 0, there exists, this backwards E means there exists a delta that's greater than 0, such that the absolute value of x minus a is less than delta implies the absolute value of f of x minus L is less than epsilon. Okay. This is called the epsilon delta definition of a limit. Okay. So really another way to look at this is look at the intervals L minus epsilon and L plus epsilon here, and this delta window, delta minus A and then delta plus A, right? So for any epsilon that is greater than 0, so if we have an epsilon interval centered at L, we can figure out a delta that's small enough so that points are getting closer and closer to L, right? And we can readjust the length of our interval by just taking an epsilon value that is infinitesimally small, right? And we'll figure out what delta that is required to be in that epsilon window of L, right? So hopefully the geographic definition of that makes sense, right? Or I should say graphically. So in terms of complex numbers, we are going to deal with multivariable functions, right? Because after all, right, a complex function is broken down into real component, a real function plus an imaginary function, v. Okay. So the limit of a complex function will correspond to taking epsilon neighborhoods in the W plane, right? So if I have this region, okay, which is defined by f of z, right? What we're going to do now is we're going to take epsilon neighborhoods, okay? And an L this time would be a point in our function, right? So this time, this would be the circle f of z minus L is less than epsilon, right? So this is the epsilon neighborhood. Neighborhood being a disk. Okay. And then the call and response action would be, so if I have a point A, so the delta would be, so so this time we will have what's called a delta neighborhood. Right? But the definition of figuring out the limit is just the same, right? X minus A is less than delta will correspond to a delta neighborhood in the complex plane, right? And then the epsilon neighborhood here would correspond to the epsilon neighborhood in the complex plane, right? So if we vary the amount of our radii, right, we would get values that are getting closer and closer to L. Okay. So I'm not going to worry about the epsilon definition, delta definition of the limit of a complex function. Because I'm going to approach this from a calculus standpoint. Okay. And it's pretty straightforward. Okay. So limits in 2D, let's look at that in closer detail. So if I have a point in the complex plane, let's say Z naught, well, in single variable calculus, there's only two ways to approach to a limit. You can approach it from the left, or to the right. Okay. I'm not sure if this camera is mirrored, but you get what I mean. So there's two directions. You approach a point from the left or from the right. And if the limit equals to each other, then you can say the limit exists. But limits in 2D, well, it's going to be a little bit more challenging because we can approach points in 2 dimensions. Well, we can approach it in this direction. We could approach a point in 2D in this direction, right? We can approach Z naught from, let's say, y equals x, or y equals minus x, or we can do some squiggly pattern. We can do like a spiral. We can approach it at some exponential. So in other words, there are different ways to approach to a limit. Okay. And the possibilities are limitless, literally. So there's going to be a test for non-existence of limits. And it's going to be the same idea as in Calc 1, right? Because in Calc 1, right, limits approaching from the left or the right, they're two separate paths. And if those paths don't equal to the same value, then your limit does not exist. So we're going to approach this with the same mindset in looking at limits of functions in single variable calculus. So here's the test. If the limit as z goes to z naught of f of z equals to L1 along some path, call it P1, and the limit as z approaches to z naught of f of z equals to L2 along some path P2, and L1 does not equal to L2, then the limit does not exist. It's that straightforward. Okay? It's that straightforward. So let's look at this example in action. All right. So if I show that the limit as z approaches z naught of z bar divided by z, we want to show that this limit, I should say 0. As z approaches 0, z bar divided by z does not exist. Right? How do we do it? Okay, so we want to look at two paths, right? Let's say we go along x equals 0, right? So so if I look at the z plane, here's 0. Let's say we want to approach 0, let's say along the real axis. So let me change this to y equals 0. So if we approach 0 along the real axis, okay, along the real axis, right? Okay, so then, well, y is 0, so that means the limit z approaches to z0 of z bar divided by z, well, this equals to 0. This equals to the limit as z goes to 0 of, so x plus 0i conjugate divided by x plus 0i, right? Well, this equals to 1, right? So this is P1. The second path, let's say we go along, let's say x is equal to 0. So the imaginary axis. So we're going to go along 0 in these directions, right? So then what that means is the limit as z goes to 0 of z bar divided by z is equal to the limit as z approaches 0 of 0 minus y times I divided by 0 plus yi, right? So this equals to minus yi divided by yi. Okay, and so this would equal to minus 1. Minus 1. So these values do not equal. Do not equal. And so we can say that the limit does not exist. Okay, does not exist. Okay, so the properties of limits of functions that you've seen in Calc 1 or Calc 3 rather, it will be the same when looking at properties of limits in the complex functions. Okay, so let me write these out. So let f of z equal to u of xy plus I times v of xy. So we can express a complex function in terms of the real and the imaginary components. That's what I'm saying here. Okay. Z naught equals to x0 plus I times y0, and then L is equal to u0 plus I times v0. Okay. Then the limit as z goes to z naught of f of z equals to L if and only if the limit as x0, I'm sorry, xy approaches to x0, y0 of u of xy equals to u naught, and the limit of xy goes to x0, y0 of the v function, v of x0, y0. I'm sorry, v0. v0, excuse me. That's something different. So u0 and v0, okay? So for example, if I have this problem, z goes to 2i of z squared minus z bar. What's that equal to? So yeah, I want you to work on this on your own for a little bit. Okay, it's not that too difficult. Okay, so I assume you worked on this. We can just express z squared minus z bar in terms of the real and imaginary components. So this will correspond to the limit as xy goes to the point 0.02. We have 2i here, so that will correspond to the point 0.02 in the complex plane. So this would be x plus iy squared minus x minus iy. Okay, x minus iy. And so this will equal to this limit 0.2 of x squared minus y squared minus x plus I times 2xy plus y. If we wrote out this function here in terms of the real and imaginary components, it will look like this. Okay? The real and imaginary components are polynomials. Okay, so it's just direct substitution back in Calc 3. So just plug in 0 for x and 2 for y, respectively. So we will have minus 4 plus 2i here. So that will equal to minus 4 plus 2i. Okay, so pretty straightforward. And also we'll look at different properties of complex limits. And it will be the same as you have seen in Calc 3, right? Suppose that the limit as z approaches z naught of f of z is L, and the limit as z approaches z naught of g of z equals to m. Then the following is true. the limit as z approaches z naught of a constant times f of z is equal to c times L. C is just a complex number. It's a constant. Second, the limit as z approaches z naught of f of z plus or minus g of z equals to L plus or minus m. 3. The limit as z approaches z naught of f of z times g of z equals to L times m. And then 4. The limit as z approaches z naught of f of z divided by g of z is equal to L divided by m, provided that m does not equal 0. Okay? Not equal to the 0. Okay? So one example to show this is this one. So evaluate this limit. Z approaches to 1 plus I of z squared plus 1 divided by z squared minus 1. Okay. So pause the video. I want you to work on this. Okay. All right. So I assume you worked on this example. So the z value is 1 plus I. So literally just do direct substitution. So this would equal to 1 plus I squared plus 1 divided by 1 plus I squared minus 1. Okay. And so this would equal to, we will have 1 plus 2I minus 1 plus 1 over 1 plus 2I minus 1 minus 1. Okay. And so, so this would be 1 plus 2I. Oh, let's see. Yeah. So, yeah, 1 plus 2I divided by minus 1 plus 2I, right? And to write it in a plus bi form, remember we multiply and divide by the complex conjugate of the denominator. And so, so we will have, so 1 plus 2 on the bottom, and then we will have minus 1, minus 2I minus 2I, so minus 4I, and then minus 4I squared, so plus 4. So that would be 3 minus 4I over 3. Okay, so that's what that limit equals to. All right. So the next thing I want to talk about is continuity. Continuity of a complex function, right? And essentially it means this. So limit as z approaches z naught of f of z equals to f of z naught. It's essentially what it means. Okay. So there's 3 criteria to show this, right? First of all, we need to show that f of z naught is well defined, right? The function is defined at z naught. Second, the limit as z approaches z naught of f of z exists. And the third criteria is that the limit as z approaches z naught of f of z is equal to f of z naught. It's essentially the 3 criteria we need to show. So an easy way to show that a function is discontinuous, well, it's easy to show that a limit does not exist. Okay, so for example, and the most obvious thing to show that a function is discontinuous, usually it happens with rational complex functions, right? So check where the denominator is 0, right? So like this example, f of z is equal to 1 divided by z squared plus 1. So this function is discontinuous. Discontinuous being not continuous, right? Not continuous at z equals I and z equals minus I, right? Z equals I squared to negative 1, so that would cause problems in this example right here, right? So, and then real quick, I'm just going to write properties of continuous functions. Meaning complex functions, right? Complex functions. So if f of z is equal to u of xy plus I times v of xy, and then z naught is equal to x0 plus I times y0, then f is continuous. This double arrow sign means if and only if. Okay, if and only if the limit as xy approaches to x0, y0 of u of xy is equal to u of x0, y0. And the limit as xy approaches to x0, y0 of v of xy is equal to v of x0, y0. Okay? So a complex function is continuous if and only if the real and imaginary component functions are continuous. That's what it's saying. That's what it's saying. Okay. And let me write out the different properties of continuous functions. So if f and g are continuous at z naught, then a constant times f is continuous at z naught. Okay, 2, 3, and then 4. F plus or minus g is continuous at z naught as well. Okay. The product f times g is also continuous at z naught. Okay. Just drop my pencil. And f divided by g is continuous at z naught, provided that g of z naught is not equal to 0. Okay. And also, complex polynomials, a sum of coefficients and powers on z are continuous. On the entire complex plane. Okay, on the entire complex plane. All right. So let's look at an example of when a function is not continuous, right? So and we're going to look at a very special function, the square root function. Show the function f of z equals z to the 1/2 is discontinuous at z naught equals to -1. Okay. So so if I draw out the unit circle, the z naught equals 1 would be this point there. So z naught, -1, 0 would be that point there. Okay. All right. So to show that a function is discontinuous, all we have to do is to show that the function f of z does not exist as a limit at z naught equals to -1. Okay. And then we're going to use the two-path test to do this. Okay. So if I look at the first path, where we will examine limits on this section of the circle, right? So that will constitute having the principal argument at pi over 2 up to pi. And then the other path, this will constitute to having points that are in this section of the circle. So whose argument, principal argument, is at minus pi and up to minus pi over 2. Okay, let's see what this looks like. So in terms of polar coordinates, z to the 1/2, this will equal to r to the 1/2 times e to the I, shoot, times the principal argument divided by 2. So that's the definition of the square root function in the complex numbers. Okay, so let's look at what these equal to. So if I look at so this section here, this is the point -1, 0. So we're approach. So we're going to approach along this path down here, right? So so we'll have r to the 1/2 e to the I times the argument of z over 2. Okay, so remember the z naught equals to -1. This will correspond to the polar coordinate e to the I pi, right? E to the I pi. So the radius would still be 1, right? So so f of z, this, so f of z naught, right? So this would equal to so minus pi to pi. So this would equal to 1 times e to the I pi over 2. Okay. So f of z naught will correspond to that point. So that means this would be minus I. I'm sorry, at I. Okay, cosine of pi over 2 is 1. Sine of pi over 2 is 1. So it will constitute to this point I in the W plane. Okay, so will correspond to this point here. However, if we look at the second path, which would be this section of the unit circle, right? Okay, so if we approach it along that path, and just reminding ourselves that this is the square root function, right? Of z over 2, right? So what that would mean is that so this is the other angle. So minus pi over 2 is less than so minus pi over 4, right? So Yeah, so it'll be yeah, so that would constitute the argument of z over 2. Okay. So if we approach values this way, what that will mean is that f of z naught in this case, well, this would be e to the minus I pi, right? So this will also would equal to minus I. So it'll be a point that's down here. Okay, so these values don't equal, so we can say that well, the limit for z naught equals to -1 does not exist. Since that limit does not exist, f of z is discontinuous. At z naught, right? And as you notice, it's not even a function to begin with, because and well, that's because of the limits for our principal argument in our two different paths, right? And also this refers to the fact that if we rotate a certain 2 pi, a multiple of 2 pi of theta, we would get the same result for the square root function, or even the coming up soon, the logarithm function of a complex number. So what we need to do is think about what it means to be a function in the complex plane in regards to periodic functions. And so this will involve looking at what's called a branches, and taking branch cuts in the complex plane. So we will use lowercase letters with subscripts to indicate a branch cut, or the branches, I should say. Right, so like F1, F2, F3, and so on. Okay. And then what a branch cut is, we'll go over this in much detail. So a branch cut, it's a portion of the curve which is excluded in the domain of F. So in the example of the square root function, the branch cut, they refer to this as the principal. It's the set defined branch cut is where minus pi, where theta is in between minus pi and pi. Theta is the principal argument of z. Okay, theta is the principal argument of z. So this here is what's called a branch cut. The branch cut of this square root function. Okay. And then not only that, we can take multiple branch cuts and still have a defined function for the square root of z. So we could also take like minus 3 pi over 4 to 5 pi over 4. I believe that's another branch cut of the square root of z. And you would still have a defined function for the square root of z. Okay, what's important here is that one input in your domain will get mapped to one output, exactly one output, right? It's not, so it's similar to the vertical line test, right? Vertical line test looks at if a region is a function, right, in 2 dimensions, right? So if you draw in a vertical line and if it passes the graph more than once, it's not a function. So like an example like this, right? We have one input that's mapping to 2 different outputs. So that's not a function, right? So it's the same concept, but we are just building upon branch cuts and restricting our functions so it will be defined. So, okay. I want you to work on these problems for a comprehension check. Just to check comprehension. So 2, 6, 8, 12, 13, 14, 17, 28, 30, 31, 35. And if you have questions, let me know. I hope you enjoyed this. Thank you for watching. And I will see you all in the next video.